Hi, my name is Matt.
And I am Max.
And I always sleep with my curtains open. And today I will tell you a bit more about data collection. In the lectures, Tanier only briefly mentions data collection.
Just because we can monitor in so many places and collect so much data, a whole new world of applications open up.
And after this he continues with a small example about Teslas. That is basically all that is told about data collection. However, they tell you a lot about the data analysis and privacy of this data, mainly in lecture 11, but not so much about the collection of this data. Therefore, we will show you a bit more about the missing spoke of the wheel of IoT, namely data collection.
Companies have different options for managing the data collection process. Because of the enormous amount of data that is collected today from the enormous amount of IoT devices in use, the management process has become a very subtle process of ordering and handling the enormous data flow correctly. There are a multitude of options for prioritizing different aspects of the data collection process. For example, do companies want to maximize the amount of data collected, or do they want to maximize its quality? And are you okay with them neglecting your privacy in order to do so? In this presentation, we will look at different up and down sides of different prioritization approaches and see why some are better than others. Different focus requirements may be more suitable to different applications. Environmental monitoring networks, for example, are highly dependent on their data collection being accurate. News networks can catch a lot of flack nowadays for not estimating the weather correctly. Nobody wants to think it's going to be sunny on their Tinder date for it to actually start pouring with rain in the middle of your picnic.
For applications where weather data is collected, timeliness is not of big importance, but accuracy is. There are other applications, however, like security of infrastructure management, where timeliness is of greater importance and accuracy can be neglected a little bit. For example, you don't want to know that somebody has broken into your house 2 hours after this happened, because then they might be already gone.
As discussed in the lectures, some IoT devices also run on batteries. This means that, in addition to the previous two strategies, some developers also need to take energy consumption and energy management into account. This is not only true for IoT devices that run on batteries, however. Elon Musk's IoT satellites cannot consume more energy to function than can be produced by their solar panels.
Finally, there has been much talk about privacy lately. Tesla, Google and Facebook and many other companies are getting into trouble for not keeping your data private. The same should go for data collection in IoT networks. For example, most people do not want Samsung to know that you opened your smart fridge at 4 AM last night.
We know what you did.
Therefore, for privacy-sensitive applications, we require a means of data collection that is private and maintains the quality of your data.
The paper we will discuss in this bathrobe joke is getting kind of old, right? The paper we will discuss in this presentation performs different experiments with different protocols that kind of prioritize different of these requirements.
The strategies developed by the authors are implemented on the Fiesta IoT platform. In short, this means that the strategies are run on the data collector side. In practice, this is realistic as the sensor nodes often have limited storage and processing capabilities.
Now that we've seen different approaches to data collection, let's look at how the authors of the paper actually proposed some protocols to actually handle these approaches. We'll start with the accuracy-driven data collection. The authors propose a protocol that considers a trade-off between data accuracy and frequency of measurements. They propose some bound on the accuracy that kind of measures the difference between the actual sensor value and the last measured value. Then they propose that each time this bound is exceeded, so that means the the lastly measured value is inaccurate to some degree, they propose there should be some measurement that takes place. In a perfect world, with some system that is able to measure both the past, the present state, and the future, that would be optimal in a state where the inaccuracy of the last measured value, when that kind of exceeds the inaccuracy bound that is set by the users, I guess, then at that exact moment the measurement would take place. Such a perfect information system is known as the oracle system. Oracle systems are obviously not possible in real life, as they require future information which we do not have access to yet. The authors, however, propose a method that actually counteracts this issue. The method proposed by the author uses a dynamic time interval between measurements, such that we can periodically check whether we are still within the accuracy interval. Consider this graph. The green line here displays the time interval between measurements in the method proposed by the authors. There are two options when a measurement takes place. Either it falls within the accuracy interval or it falls outside of the accuracy interval. If the measurement falls within the accuracy interval, it means that we shouldn't have measured yet because, the previous measurement was still fine. So we increase the time interval between the measurements such that the future measurement is done, after more time than this measurement was done after. If the measurement falls outside of the accuracy interval, however, it means we should have measured earlier, because now we have exited the accuracy interval. As such, the time interval is halved, such that future measurements are done more frequently. This method is not something that's new, and the most common protocol in which it appears is the AIMD protocol. And this is also the protocol on which the authors carry out experiments in the rest of the paper.
In time-sensitive IoT networks, we require a protocol that aims at minimizing the time difference between requests without making it too costly. In an ideal world, we would just simply measure the data continuously. However, this is not possible in our Fiesta IoT model. Even with a very small time step between measurements, it could still be too resource intensive. Therefore, we need to have a more realistic solution to this problem. The authors describe a strategy that aims at keeping the time interval between two measurements between some maximum interval. In an ideal world, the response time of a request will be 0, and then we could just sample the data with a period equal to this maximum interval. This, of course, is not possible, since we always have some response time, and therefore we should just send the request just before the deadline. To determine this value that we need to send before the deadline, we calculate the average and distribution of the measurement platform. A user can then use these values to determine what it wants. So the user should choose between either having an interval closer to this maximum interval or making sure that more requests and responses lie in this maximum interval. Sadly, it's not possible to use both at the same time.
For energy-driven data collection, we want to maximize the net benefit, where the net benefit is defined as the gain in utility of some data minus the amount of energy it needs to actually achieve this utility. For most applications, there's some goal utility for which exceeding this goal utility would be redundant. For example, with accuracy, you may want to reach some goal accuracy, but achieving accuracy that is even more accurate than the goal you set would be unnecessary, really. An example of this would be a smartwatch, for example, which is often capable of measuring your heart rate. Very small changes in heart rate, however, for example 0.1 beats per minute, are not very interesting for the user. So we rather not measure these very small changes in order to preserve battery life. Significant changes, however, should still be noticed by the watch. This means that for most applications, we want to get as close to the goal accuracy, or more general, goal utility as possible, while minimizing the energy consumption.
The privacy-driven data collection strategy aims at making a trade-off between accuracy and timeliness and the privacy of the individuals while doing measurements. The approach works by adding noise to data. This compromises the accuracy of data, while the statistics of the overall data remains similar. You could see it like this. When Samsung queries your smart fridge if it was open last night, the fridge has a 50% chance of returning the actual answer, yes or no, or returning a random answer, yes or no. This way, Samsung will never know for sure if you opened your smart fridge. However, using simple statistical methods, there can still be horizontal analysis performed over this data to mitigate the noise. An actual protocol developed by Google is called Rappor. This is used to extract user information from Google Chrome. The authors use this approach to evaluate their protocols.
In order to perform practical experiments on the proposed protocols in the previous section, three different data types were used: temperature, humidity, and ozone concentration. These three data types were measured in three different locations as well. One testbed in northern Spain, one in Apulia in Italy, and one on Crete, which is an island part of Greece. The results obtained by the accuracy-driven protocol AIMD, which is henceforth referred to as the ADAPT protocol, is compared to an all-knowing oracle system. Here we can see two graphs, where the real sensor temperature data in blue is compared with the ADAPT protocol, displayed in green, and the all-knowing oracle system, here the red line. We can see that the ADAPT protocol needs more samples than the oracle, but the overall trend of the data is followed quite nicely. The results for the humidity and ozone concentration data are given in mere tables in the paper, which paint the same picture as these graphs do. Therefore, it can be concluded that the ADAPT protocol is quite robust for measurement of different data types, and that the ADAPT protocol can follow trends of these values quite nicely. Additionally, in the conclusion of their paper, the authors claim that the ADAPT protocol requires no tuning parameters, which is mentioned as a positive feature of the protocol. Yet the initial time step or unit time chosen might have a significant impact on the accuracy of the protocol. This makes this claim inaccurate. However, this does not take away from the fact that the ADAPT protocol is a solid technique to achieve great results for accuracy-driven data collection.
In contrast to Max, my mouth is actually in sync with the audio. But let's talk about the evaluation of the time-driven data collection strategy. One of the downsides of this strategy is that a lot of samples must be performed before we can establish a good average and distribution of the platform. So this means that in the beginning the interval size might not be optimal, but as time goes on this size will converge to one value. At the top of these two graphs you see actual data for delays of data, so the response time of data, and on top you see the interval that is determined on this data, so all that's coming in front of it. One of the interesting things here to note is that after the first big delay at t equals around 25, we've seen that the algorithm immediately compensates for this by reducing the interval size, because it might happen that more of these large delays happen in the future.
A quick intermission here, guys. We really want to know how many of you actually watch this presentation fully. So if you do actually watch it fully and you see this, please use the word extraordinary in the last rubric category in your kind of evaluation there. If you didn't think it was good, you can just use extraordinarily bad. So you can actually use that word. And let's actually see who watches these presentations fully. Thanks. In the experiment for the energy-driven approach, the authors only consider applications which have some goal utility. This means that any utility that exceeds the goal will be considered to be exactly equal to the goal utility. The utility here will be considered to be equal to the accuracy. The net benefit which needs to be maximized will be computed by taking this utility and subtracting the energy cost from it.
Look at this graph.
It shows the results from the experiment. Here we can see three lines. We plot the utility, which is in this experiment equal to the accuracy. We plot the energy cost, which is computed by taking the frequency of the measurements necessary to actually obtain this accuracy. And thirdly, we plot the net benefit. The authors conclude from this graph, and similar other graphs which are given in the paper, that the net benefit is the highest when the utility is exactly equal to the goal utility, which is kind of to be expected, I guess. The authors also go on to compare the approach to the Oracle system and conclude that the results obtained using this method are pretty close to the Oracle, which would imply that the approach is pretty good.
Finally, we look at the privacy-driven data collection strategy. The authors evaluate how the addition of noise changes the data of a large set of sensors. As can be seen in this picture, the data without noise does not deviate much from the data with noise. Therefore, we can say that this technique is especially applicable for applications where horizontal analysis is needed, while maintaining the privacy of one individual, because the average of the changed data does not differentiate much with the actual average, and the data of one individual does not say much. On the flip side of the coin, vertical analysis can no longer be performed on this data because data of one individual has nothing to say.
Now that we've seen the experiments and the evaluation results as well, let's look at how the paper concludes these. The adaptive accuracy-driven approach in the paper has been presented in a concise manner, and the experiments seem to show that the approach is very robust for measurements of different data types. Additionally, the experiments of the privacy-driven strategy have shown that, despite the small number of sensors, the addition of noise to the sensor measurements has an insignificant effect on statistics. Unfortunately, the authors failed to provide conclusive statements in the time-driven and energy-driven experiments. There is a clear gap in the conclusions, which makes one wonder why the experiments were included in the first place, as they do not seem to find any conclusive results. For specifically the privacy experiment as well, the datasets used were quite small. This may induce some skepticism in readers, as the results may be skewed because of the small size of the datasets. However, overall, the paper has some quite conclusive results, and we think the protocols presented were still very robust.
Well, that was it, guys. Thanks for watching. I hope you enjoyed. Don't forget to leave a like and subscribe, and then we will see you at the Flippity Flop.